Hello everyone, very good evening. Kindly confirm if audio video is clear. Good evening everyone. Audio video clear. Okay. So let's begin with the sixth lecture. Let's begin with the sixth lecture of relational model and normal forms. In the last class, we have understood the concept of closure of an attribute set. Okay. So, closure of an attribute set is actually a set of all attributes that can be determined by the attributes of the given set. Okay, so all the attributes that can be determined by the attributes of a given set will be called closure of that attribute set. Now, if you have a set of attribute whose closure contains all the attributes of the relation, then that set of attributes will be called a super key, because super key is actually nothing but a set of attributes that can determine all the attributes, right? So if you have a set of attribute whose closure contains all the attributes of the relation, then you got your super key. Now the only thing that you need to check whether that super key is minimal or not. So if none of the proper subset, if none of the proper subset with respect to set of attributes, which is actually your super key. So if none of its proper subset is a super key, then it means that the set of attributes that you got as a super key is minimal, and hence it will also be a candidate key. Clear? So that's what we defined with respect to closure. Now there may be more than one candidate keys, that's fine. But today, in the last class, we have seen three examples, and I gave you some homework problem to identify the candidate keys of those relations. So we'll see those homework problems, and then we'll see that given the candidate keys of a relation, how can you identify the number of super keys possible for the given relation? Okay, so please tell me, do you have any doubt with respect to closure concept or the super key concept, that is the set of attributes that can determine all the attributes, proper subset concept, the closure with respect to proper subset, and if none of the proper subset is a super key, then it will become the candidate key. If any of the proper subset is also a super key, then the original set is not minimal, and hence it will just be a super key but not a candidate key because it is not minimal. So any doubt related to concept of closure, super key, candidate key? Please ask Nishchal and Sneha to refresh their page. Come on. Everything is okay because I am also able to watch the session on the web, so there is no problem from my side. If at all there is any issue, then it must be at their end, or they, yeah, they are yet to refresh the page. Yes, start. So any doubt? Please make sure that after every week of class you will get one weekend, so it's your responsibility to revise the content of that week in that weekend, and if you have any doubt, please ask in the very next class. If you don't do it, then there will be a lot to revise and you will never be able to complete the subject on time along with me. So there are some strategies that you must follow in order to complete the syllabus in the given period of time. Otherwise, you can study DBMS for the whole year. It does not matter. Okay. So the attributes that are not present in the right hand side part of any functional dependency will be called essential attribute, and every essential attribute must be present in every key. People are confused between essential attribute and prime attribute. Every essential attribute will be prime attribute, but every prime attribute need not be essential attribute. Every essential attribute, because it will be present in every candidate key, therefore every essential attribute is guaranteed to be a prime attribute, but the prime attribute need not be an essential attribute. So sometimes the set of prime attribute, sometimes the set of essential attributes itself will become the candidate key, right? So this is what happened in this particular example, that A and B are essential attribute. When you calculated the closure of AB, you got all the attributes, and we know that because both A and B are essential, therefore none can be removed. Therefore, we can directly say that AB will be the candidate key. And because none of the prime attribute is present in the right hand side part of any FD, therefore relation will have only one candidate key. So that's what I mentioned. If none of the prime attributes appears in the right hand side part of any of the FD, then the relation will have only one candidate key. Clear? Come on, here. So here again, B is your essential attribute, and if you look at closure of B, closure of B will contain all the attributes. Therefore, the essential attribute itself happened to be candidate key. Now, B is essential, so it will not appear in the right hand side part of any FD. Therefore, B will be the only candidate key. If you start from somewhere else, then also you will reach to the same candidate key. There is nothing wrong with that. Okay. Then I said that what if the prime attribute is present in the right hand side part of some FDs? So if prime attribute is present in the right hand side part of some FDs, then the corresponding prime attribute can be replaced by the left hand side of that FD in the corresponding candidate key, and by doing so you will get a new super key, and perhaps it will be a new candidate key, and perhaps from there you will find a new candidate key. Clear? Is this clear that X implies Y? So if Y is the part of candidate key, then whatever that can be done by Y can also be done by X. So in that key, you can replace Y by X and you will get a new super key, and with respect to that, you may find some new candidate keys as well. So if there exists at least one FD in which the prime attributes appears in the right hand side part of some FD, then that relation will have at least two candidate keys. We have seen the example. So this is your relation. Then we come to know that AB is our candidate key. So the very first set of prime attributes will be AB. Now, A appears in the right hand side part of this FD. Therefore, we can replace A by D in the corresponding candidate key AB, and you will get DB as a new super key. When you check that DB is minimal or not, you will get to know that DB is minimal. Therefore, DB is a candidate key as well. So after that, the set of prime attributes will increase in size. Some new attributes may get inserted into the set of prime attributes. Now the prime attributes will be A, B, and D. Now when you check with respect to this FD, you will get to know that AB implies CD we can split it into AB implies C and AB implies D. C is not a prime attribute, but D is a prime attribute. Therefore, if you replace D by AB, it will be ABB, which is same as AB, and it was already a candidate key. Therefore, no other candidate key is possible because there is no other possibility of replacement. So as of now, I don't think there is any doubt to anyone. If you have any doubt, please ask. Vivek, it will be better if you try to finish the previous lectures as soon as possible, because most of the things will not make sense to you if you start watching the lecture from here itself. So don't do it. Don't waste 2 hours of time. Only 5 lectures are passed. So you will have to put some extra efforts and you will have to complete them as soon as possible so that you can become regular with the live classes. Okay, Vivek. So, I mean, it's better if you utilize this 2 hours to complete some previous lectures. Otherwise, you will again have to watch the same lecture. So, don't do it. I know homework. If I give you any homework problem, I'll definitely discuss it in the next class. So, don't remind me of the homework question. I'm just asking, do you have any doubt in the previous 5 lectures? Just answer that simple question. If you have any doubt in the last 5 lectures, you can ask. Otherwise, we'll begin with the remaining part of this lecture. No? And somebody asked that, sir, if we already have a set of essential attribute, why do we have to calculate the candidate key, or why do we have to look for the candidate keys? Because sometimes the set of essential attribute alone need not be the candidate key. It just happened that B is the only essential attribute, but B alone is not a candidate key. You may have to include some other attributes along with the essential attributes in order to specify the candidate key for that relation. Yeah. Okay. Let's begin with the today's topic. So the very first homework problem that I give you is this. What are the candidate keys for this relation? What are the candidate keys of this relation? See, you need to find all the candidate keys. You need to find all the candidate keys. If you find one and you don't find some, if any of the candidate key is not found, then your set of prime attributes and your set of non-prime attributes will be incorrect. Okay? No, only PO is not the candidate key. Please try to understand. Sir, O is essential attribute. And we know O closer will be O only. Therefore, O alone cannot be the candidate key. O alone cannot be the candidate key. Right? So, it is not a super key. Something which is not a super key cannot be a candidate key. Okay. Let's check for the candidate key. So very fast candidate key, very fast super key you can find intuitively. You can actually see that if you take MNO, then by MNO, M, N and O are already present, and you will be able to determine P and Q as well. So if I simply check for the closure of M, N, O, yes or no? First super key you can find intuitively. So M, N, O will be M, N, O, P, Q. I'm not saying that this is the candidate key. I'm just uh, finding the very first super key intuitively so that I can reduce the size of that super key if required, and I'll be able to find the candidate key of that relation. So I hope you understand that MNO closer will be MNOPQ. So from here we get all attributes. Therefore, MNO is a super key. MNO is a super key. Now, please look at this. Sir, check for candidate key. Okay, some important thing that you must understand. How many non-empty proper subsets are possible of a set containing 3 attributes? How many non-empty proper subsets are possible with respect to this set? how many proper subsets are possible with respect to this set MNO? Non-empty, if I say 6, one is empty, so non-empty proper subsets will be 6. Now the idea is, do we need to find the closure? Do we need to find the closure of all those 6 non-empty proper subsets? Please tell me. Do we need to find the closure with respect to all those non-empty proper subsets? No, sir. O is essential, therefore you don't need to check with respect to proper subsets in which O is not present. O is essential, therefore you don't need to check for proper subsets in which O is not present. You don't need to check for proper subsets in which O is not present. Yes or no? So you only need to check for two proper subsets that will include O as well, and that will be MO and NO. Because if O itself is missing, it can never be a superkey. If O itself is missing, then it can never be a superkey. Clear? So, sir, other proper subsets will be M, not required, N, not required, Mn, not required, O alone is not required, because O alone was the superkey, then you will not even look for this. Yes or no? So this 4 proper subsets, you don't need to check closer with respect to this 4 proper subsets, because 3 of them does not contain O and one is O alone, which is already, with respect to which we have already checked that it is not a superkey. Clear? So when we check with respect to proper subset, please make sure that all the essential attributes are present in all those proper subsets, otherwise they can never be superkey. Done? Okay, so what will be MO closure? So MO closure will include M and O. Now, LHS MNO is not the proper subset of MO. LHS is not the proper subset of MO, therefore done. So NO will be NO only. So we come to know that no proper subset of MNO is a superkey. Therefore, MNO is minimal. So what do we get to know? That MNO is a candidate key. We have found our first candidate key. Who said that PO is the only candidate key? Now, do they understand that MNO closure also contains all the attributes, and none of the attribute can be removed from the set MNO without destroying its property of being a key. Therefore, the set MNO is also a minimal superkey. Therefore, the set MNO is a candidate key for this relation. Clear? Everyone? So, if MNO is the candidate key, then what are the prime attributes with respect to MNO? Will be M, N, and O. Clear? Now the next thing that you must understand, that sir, we have a functional dependency P implies Mn. So whatever that can be done by M and N together can also be done by P. Whatever that can be done by M and N together can also be done by P. How do I explain them? Pragya, Sneha, even you ask me that sir, the video is not available. I cannot give any solution to you because whatever I'll say, you will not be able to listen to me. So please listen to your fellow students. They are asking you to refresh the page or terminate the session, log in once again and try to access the video. Come on. Sneha, if application is not working, please. Om. What makes you think that MNO is not minimal? Why are you saying that, sir, MNO is not minimal? What makes you think that MNO is not minimal? Huh? What makes you think that MNO is not minimal? When I just said that no proper subset of MNO is a super key, then for MNO is minimal only, right? Oh, when did I say that minimal will contain minimum number of attributes? Minimal is a property associated thing. Minimal has nothing to do with the number of elements in the set. Did I ever say that minimal key should contain minimum number of attributes? Did I ever say so? It's your imagination and your assumption. I never said that it will contain minimum number of elements. I only said that it should be of the type such that nothing can be removed from it without destroying the property. I never told you anything about the number of elements in the set. I only said that nothing should be removed from the set without destroying its property, and from MNO, nothing can be removed from the set without destroying its property, so it is minimal. Minimal, maximal has nothing to do with the number of elements. They are associated with the property. They are property based thing. These two terminologies, minimal and maximal, are the property based terminologies. They have nothing to do with the cardinality or size of the set. That how many elements are there. So whatever that can be done by M and N together, whatever that can be done by M and N together can also be done by P. Sneha. Whatever is in the RHS, replace it by the LHS of that particular FD. So what will you get after replacement? If you replace Mn by P, you will get to know that PO is a super key. Now, do we need to check with respect to any non-empty proper subset? Please tell me. Do we need to check any non-empty proper subset with respect to PO? Do we need to check any proper subset with respect to the set PO? Think carefully. Sir, O alone cannot do the job and O cannot be removed from the set. O alone cannot do the job and P alone does not contain the essential attribute. So O is the super key, as well as we don't need to check for anything. I can directly say as well as PO is a candidate key. After this, what will be the new set of prime attributes? The new set of prime attributes M, N and O were already the prime attributes. Now P is also included in the set of prime attributes. Okay, sir. Can we replace anything else in this first candidate key MNO? No, sir. We have replaced M and both. If you replace only M, then it will become PNO and N will be redundant. You will you will have to remove the N from the set. If you replace N by P, then M will become redundant and you will have to replace M from the set. But here, you know that, sir, this is actually equivalent to MNO implies P and MNO implies Q, and here P becomes a prime attribute. Here P becomes a prime attribute. Therefore, in this candidate key, we know that MNO implies P. Therefore, replace P by MNO and you will get the same candidate key which is MNO. And you will get the same candidate key which is MNO. Is there any other possibility of replacement? Is there any other possibility of replacement? No, sir. No other possibility of replacement. So can I say in the above example, MNO and PO are the only two candidate keys of the relation. So once you have identified all the candidate key, you will be able to define the set of non-prime attributes as well. You have already found the set of prime attributes to be the set containing four elements M, N, O and P. Now, the non-prime attribute is the attribute that does not appear in any of the candidate key, and the only such attribute is a Q which is not present in any of the candidate key. Therefore, Varnekar, stop preparing for the GATE exam. Okay? Stop preparing. If you are not able to understand that MNO is minimal, then you can stop preparing. After specifying so many times that MNO is minimal, if you are still saying that MNO is not minimal, you can stop preparing. What's wrong? Why waste time? You cannot join the session as per your convenience and can say that, sir, MNO is not minimal. I'm not going to repeat the same thing again and again. Hmm? Okay, done. Next question. What are the candidate keys of this relation? So some got only two candidate keys, some got 3 candidate keys, and some of you even got 4 candidate keys. So as I said, you need to check for all possible replacements. You need to check for all possible replacements. So let's solve this question at the next slide. So we have relation R with attributes A, B, C, D. FD set F happens to be AB implies CD, and I believe C implies A and D implies B. C implies A, D implies B. So there is no essential attribute because all 4 attributes are present in the right hand side part. No essential attribute because all attributes are present in the right hand side part. So it is not necessary for any attribute to be present in every candidate key. Clear? So we'll start intuitively. We know so that AB implies CD contains all the attributes. We know that AB implies CD contains all the attributes. So the moment we check for the AB closure, we know AB closure will contain all attributes. AB closure contains all attributes. Therefore, AB is super key. I'll not write all the time, but simply, sir, you don't have to write this. Sir, A closure will be A only, B closure will be B only. Sir, A closure is A, B closure is B. No proper subset of AB, no proper subset of AB is a super key. Therefore, I can say AB is a candidate key. And the moment you identify this very first candidate key, therefore, the prime attributes will be A and B as of now. As of now, we have only 2 prime attributes, A and B. Now the next thing is, the prime attribute A is present in the RHS of C implies A. Prime attribute B is present in the RHS of D implies B. So you have 2 different paths. You have 2 different paths. One is, say, sir, C implies A, and this A is prime. Therefore, replace A by C. So if you replace it, you will get what, sir? A replaced by C, you will get CB is a super key. As of now, I am only calling it a super key. Don't worry about it. So here, D implies B, where B happens to be prime. Therefore, replace B by D, and you will get to know that B A T is super key. Come on, sir. Sir, C closure will be C and A only, B closure will be B only. So no proper subset of CB is a super key. Therefore, I can say that CB is a candidate key. Make sense? C closure is CA, B closure is B. CB is our candidate key. So after that, let's, as soon as you find any candidate key, you can specify the set of prime attributes. So what will be the new set of prime attributes? A, B were already the prime attributes. Now the prime attributes are A, B, C. Here, A closer is A only, B closer is D and B only. None of them contains all the attributes. Therefore, I can say AD is a candidate key. Therefore, prime attributes will be what? Sir, A, B, and C are already the prime attributes, and D has now become a new prime attribute. Therefore, A, B, C, D all are prime attributes. Now the thing is, sir, in this FD, C, forget about C, but B is still in the right hand side part. So can I replace B by D? Here, sir, C implies A, therefore we can still replace A by C. So there are two possibilities. What are they? So here, D implies B, therefore replace B by D. Here, C implies A, therefore replace A by C. If you perform any replacement, then B replaced by D will be D, CD, and A replaced by C will also be CD. So from here you will get CD is a super key. Now, when you check with respect to C closer, C closer will be C and A only, not all attributes. D closer will be D and B only, not all attributes. So, no proper subset of CD is a super key. Therefore, CD is a candidate key. Sir, already all attributes are prime attributes. So, even if you define the set of prime attributes, after that, no new attribute will be included in the set of prime attributes, because already all four attributes A, B, C, D are prime attributes. Now, please try to understand, sir. Sir, this FD is actually AB implies C and AB implies D. So what are the possible things? Okay, one more thing that you must understand. That's one more choice that was available is this. Sir, whatever that can be done, listen to me very carefully. So this, at this point of time, we know C implies A and D implies B. So we can replace A and B simultaneously by C and D respectively. C implies A is the prime attribute, D implies B is the prime attribute. Therefore, replace A by C and B by D. So if you perform this replacement together, then also you will get CD. If you replace both A and B together in the candidate key AB by C and D respectively, a new candidate key that you will find is the CD. Make sense? Make sense? Now, so here, if I check that, sir, AB implies CD, therefore you can replace here AB implies CD, therefore replace CD by AB. But even if you do so, no new candidate key will be found. Here, if you replace this B by D is replaced. If you again replace this C by AB, you'll reach to the same position. If you replace D by AB, then also you'll get the same thing. Is there any other possibility, or is there any other possible choice of replacement that can generate a new super key? Is there any other possible choice of replacement that can generate a new super key? No. So once there is no other choice left, you will say that these are the only candidate keys possible for this relation. So in the exam, should we do like oh, you will have to do all these things even in the exam, but you will not write all these things. Therefore, the calculation of candidate key will not take more than 30 seconds. So anyway, you will have to do all these things. No other solution to find the candidate keys of a relation. But while I am writing all these things, these are just for the better understanding during the revision. Otherwise, I don't have to write all these things. I can look at the FDs and I can say that what will be the candidate keys of this relation. Okay, so in the above example, AB, CB, AD, and CD are four candidate keys of the relation. Therefore, prime attribute A, B, C, D. Non-prime attributes. So there is no non-prime attribute in this relation. There is no non-prime attribute in this relation. Again, an important thing. If there is no non-prime attribute in a relation, when we'll discuss the normalization, we'll say that if there is no non-prime attribute in a relation, then the relation will be in at least 3NF. But these are the things that we'll discuss at the later point of time. As of now, you only need to calculate the candidate keys of the given relation. One step at a time. We'll learn everything, but one step at a time, otherwise too much confusion. Okay, next example or next homework problem is this. What are the candidate keys of this relation? What are the candidate keys of this relation? Most of you are correct. Ananta, you did not read the question carefully. In the relation, we also have the attribute H and E, and those two attributes are not present in the right hand side part of any FD. Therefore, E and H both should be present in every candidate key. So you cannot say A, D, AC. So your answer will be wrong. Okay, come on. So let's look at this. So what are the essential attributes? So the only attributes that are not present in the right hand side part of any FD are E and H. One more important thing. Sir, what is EH closer? What is EH closer? Sir, EH closer will be E and E can determine C. Now my question is that, sir, if in every FD E and H are present, in every candidate key, if it is guaranteed that in every candidate key E and H are present, so if E and H are present, do you ever need C in the minimal key? If E and H are present, so do you ever need C in any minimal super key? My question is, if E and H are present, then do you ever need C in any minimal super key? No, sir, because if you have E and H, then you will be able to determine C and you can eventually remove C from that set. You can eventually remove C from that set. So somebody answered the candidate key as BCEH. Malati Mane, whatever. Sorry if I pronounced it incorrectly. But Manati Mane, BCEH. So you are saying, sir, that BCEH. Now you must understand that if you have E and H, then E and H are capable of determining C. So when E and H are present, you don't really need C in the minimal set. You don't really need C in the minimal set. So the one thing that you must understand is that apart from the essential attributes, all the attributes that can be determined by essential attribute, apart from the essential attributes, all the attributes that can be determined by the essential attribute will never be present in any candidate key. Will never be present in any candidate key. Come on. Oh, sir, will never be present in any candidate key. Sir, here essential attributes, look at this. Sir, here the essential attributes were A and B. So here the essential attributes were A and B. Now, in the closure, apart from A and B, C, D and E are present. So C, D and E will never be present in any candidate key of the relation. C, D and E will never be present in any candidate key of the relation. It just happened that, sir, candidate key happens to be AB only. C, D are not required in any candidate key. Similarly, here B closer contains A, E, C, D. So A, E, C, D will not be required in any candidate key of the relation, because if any of them is present, then it is redundant, because it can actually be obtained from the essential attribute B. Okay. Here also, sir. Here also, sir, B closer is B. So no other extra attribute is there, then any of the attribute may be present in the candidate key. But the only thing that I wanted to explain here is that because EH closer can determine C, then all the attributes that can be determined by the essential attributes, all the attributes that can be determined by the essential attributes will never be present in any candidate key. All extra attributes that can be determined from the essential attributes will never be present in any candidate key. They may be present in super key, but candidate key is minimal, therefore they will not be present in any minimal super key. Got the idea? Any confusion? Okay. It's clear to everyone that all the attributes that can be determined from a set of essential attributes will never be required in any minimal super key, because Those attributes can eventually be determined from essential attributes, and essential attributes are present. Therefore, those attributes will be just redundant in the minimal set or in the set. Therefore, that set can never be minimal. So we know E and H alone cannot determine all attributes, but E and H are definitely present in every super key. Therefore, E and H will be there. E and H cannot work alone. So we thought that let's try to think that what happens if we include A with E and H. Let's check that what happens. E and H alone cannot do the job. E and H alone cannot do the job. So we thought that let's include A along with that E and H. So we said that E and H, E and H will always be there in the closure. A can determine B. E is there, therefore E can determine C. Now B and C together will be able to determine. So A, B, C, D, E, H, all attributes are there. All attributes. A, E, H is a super key. Now tell me, do we need to check for any proper subset of AEH? There are 6 non-empty proper subsets of AEH. Do we need to check for any proper subsets of AEH? Think carefully. Do we need to check with respect to any proper subset of AEH? See, E and H cannot be removed from the set, and E and H alone cannot do the task. So along with E and H, something else is required. So E and H are guaranteed to be present, and apart from E and H, something else is required. And in this case, that something else happens to be A. So A cannot be removed. So nothing can be removed from this set. Yes or no? So can I say that A, E, H is a candidate key? Please, I am directly writing it is a candidate key because I don't need to check for any non-empty proper subset of AEH. Is it clear to everyone that without checking any with respect to any proper subset of AEH, I'll be able to say that AEH is minimal. Nothing can be removed from this set AEH. Is it clear to everyone? There should not be any confusion. Unnecessarily, you don't have to check for number of proper subsets. Okay. Now, sir, once we find the very first candidate key, you will get the first set of prime attributes, and as of now, the prime attributes will be A, E, and H. The set of prime attributes will be A, E, and H. Now, E and H are not present in the right hand side part of any FD, but we know that, sir, what? A. So, D implies A. What do we have? D implies A. Therefore, replace A by D. So, you will get to know that D, E, H is a super key, as well as, again, same logic. Again, same logic. E and H are essential, and E and H alone are not sufficient enough. So someone else will be required along with E and H, and here D, E, H will be minimal. Clear? So D, E, H is a super key as well as a candidate key. So after inclusion of this, the set of prime attributes will become A, D, E, H. A, D, E, H. Now, next. Sir, let's check with respect to D. You will get to know that, sir, BC implies D. BC implies D. Therefore, whatever that can be done by D can also be done by BC. Whatever that can be done by D can also be done by the LHS, that is BC. Replace D by BC. So I would say that's a BCEH is a super key. If you are intelligent enough, you directly say that E and H can determine C, therefore C is not required. If you are intelligent enough, then you know that E and H can determine C, and when E and H are present, C is not required. Therefore, you can directly say that C can be removed from the set. Yes or no? But C is, I would rather say, EH closer contains C. Therefore, we can directly remove C. But if you don't do that, if you are not able to recall the concept, then you will eventually check for the proper subset. Now, sir, E and H are essential. Therefore, the only proper subsets with respect to which you will check will be C, E, H closer and B, E, H closer. Do you need to check with respect to any other closer? No, sir. And C, E, H closer will be C, E, H only. That is not a super key. But BEH closer will contain B, E, H from E, C, from B, C, D, from D, A, all attributes. BEH is the super key. As of now, we are only saying that BEH is a super key. Hence, BCEH is not a candidate key. If any proper subset happens to be a super key, then the original set cannot be a candidate key. Now, from here, we'll get to know that, sir, BEH is a super key. We got a smaller size. Super key, which is BEH. Now we need to check for any other proper subset. No, sir. Super key as well as candidate key. So I can definitely say that this BEH is a super key as well as candidate key. Once you found this new candidate key, what will be the set of prime attributes? So, A, D, B, E, H. Now, sir, B can be replaced by A. So here we have A implies B. Therefore, replace B by A. If you do so, you will again get the same candidate key, that is AEH. Sir, in AEH, the only thing that can be replaced is A by D. We have done that. Sir, in DH, the only replacement possible is that you can replace D by BC. We done that and we have found BH as a new candidate key. Now in BH, the only possible replacement that can be done is that replace B by A, and by doing so, you will get AEH. Is there any other replacement possible? Is there any other replacement possible? No, sir. So in the given relation, AH, BH and DH are three different candidate keys. Yes or no? Yes. Is there any other candidate keys possible? No, sir. So AH, BEH and BEH are the only three candidate keys of the relation. So once you found all the candidate keys, you will be able to define the set of non-prime attributes as well. We already found the set of prime attributes because we found all candidate keys. So prime attributes will be A, B, D, E, H. Non-prime attribute will be C. The only non-prime attribute in this relation is C. Now, I just want to ask, do you have any doubt related to candidate key concept? Homework. Yeah, I'm not going to solve those things. You can take the PYQs from your book, any PYQ, all PYQs. Please try to understand. You can take all the PYQs. Don't worry that what is being asked in the question. Don't look at the complete question. Don't look at the complete question. Don't worry that what is being asked in the question. In the question, there will be a relation, the attributes of that relation, and some FDs. Please, there will be a relation. Don't know what is being asked, but if at all there is any question in which a relation is given, along with the relational schema, the attributes will also be given. And if the FD set of that relation is also given, then you will be able to find the candidate key of that relation. You will be like, so that from where do we get the practice questions? You can take any question from any PYQ in which the relation along with its attributes is given and the FD set of that relation is also given. Then given the FD set of a relation, you will be able to find the candidate keys of that relation. That's it. So there are number of practice questions available in your PYQ itself. So as of now, don't worry that what else is being asked in the question. Just read the question. If there is a relation along with its FD set, find the candidate key of that relation. That's it. Don't read the complete question that what is being asked. Don't read the complete question that what is being asked. Just check if there is a relation and its FD set. Go and find the candidate key of that relation. Find all the candidate keys of that relation. Sir, can you please demonstrate solving this problem in the air? No other doubt. No doubt. Look at this. Sir, I'll just check that A, E, H. E, H will be there. So here is like, sir, A to B. Okay. E to C. So this will just happen with the practice. So you know E and H is guaranteed to be there. So I'll just say E and H. Then I'll say, sir, A, B. So if I include A, it will have A, B. E, H will give me C. So A, B, C. And from B, C, I'll get D. So is it clear that you will be able to check that A, H will be the key? Is it clear that by looking at this FD set, you will get to know that E and H are essential and E and H alone can only determine C. So we will have to include some other things along with E and H. So I thought, what will happen if I include A? So he said, if I include A, it will be A, E, H. E, H can determine C. So from A, E, H, you will have A, E, H, C. And A can determine B. So closer. you will never write the closure by following those steps that I explained. Just by looking at the FDs, you will be able to write the closure. Right? So I'll get to know that AH is a key. Now I'll be like AH is a key. So we know that EH and E and H are essential. Therefore, I know that nothing can be removed. Therefore, it has to be a candidate key. Now we'll know that A and D. Therefore, we'll know that DEH is another super key. But we'll check that sir E and H are essential and E and H alone alone are not sufficient. So we'll know that this is also a candidate key. Then we know that D can be replaced by BCH. So I'll write BCH. But we know that E and H are essential and EH closer can determine C. Therefore, I can remove this. So I'll know that this is also the candidate key. This as simple. Oh, not because I know this question. Once you practice 20-25 questions, you will also be pro that oh, candidate key identification of a candidate key is a silly concept. Will not take too much amount of time. Okay. Now, some relation may have one candidate key, some may have two candidate keys, some may have three candidate keys, some may have four candidate key, etc. etc. So, given the candidate keys, how do we find the number of super keys in that relation? Given the candidate keys of a relation, how do we find the number of super keys in that relation? So, the next concept is number of super keys. Next concept is associated with identifying the number of super keys in a relation. So this is the very first question. Consider the relational schema R with n attributes A1, A2, A3 up to An. Consider a relational schema R with this attributes A1, A2, A3 up to An. Find the number of super keys possible in relation R. Find the number of super keys possible in relation R. First case, when A1 is the only candidate key of relation R. So there is only one candidate key and that candidate key happens to be a set containing attribute A1 and there is no other candidate key. So how many super keys are possible? Not n minus 1, sorry. N. Okay. Very good, but wrong. Come on, guys. Any superset of candidate key will be a super key. Any superset of candidate key will be a super key. N into n plus 1 by 2. Do whatever you want. All your choice. You can do whatever you want. Who am I to stop you? Come on. Sir, what did I say? What is a super key? Super key is nothing but a set containing all attributes of at least one candidate key plus 0 or more attributes out of remaining attributes. So, there is only one candidate key. So, if I say, sir, all attributes, so there is only one candidate key. So, if I define a super key, then we are saying A1 must be present. So, the only attribute, the only candidate key is A1. Therefore, all attributes of that candidate key A1 must be present. Therefore, A1 must be present. A1 must be present, and apart from them, and so I would just say all attributes and 0 or more attributes out of remaining. So A1 must be present. If you have already chosen A1, how many remaining are there? Sir, n minus 1. So A1 must be present, and any number of attributes, any, may be chosen out of remaining n minus 1 attributes. So if I ask you for the number of super keys, so in how many ways A1 can be chosen? In how many ways A1 can be chosen? So there is only one way to select A1. Or there is only one way to include A1 in the set. And sir, in PNC, and always corresponds to multiplication. In PNC, and always corresponds to multiplication, and or corresponds to addition. So out of n minus 1, we can choose 0 or 1 or 2. So, and out of remaining n minus 1, we can either choose 0 or out of remaining n minus 1, we can choose 1, or out of remaining n minus 1, we can choose 2. Out of remaining n minus 1, you can choose all n minus 1 as well. Out of remaining n minus 1, you can choose all n minus 1 as well. Right? Now, please remember this basic formula not only in the DBMS, but it will be required in the discrete mathematics as well. The binomial expansion of 1 plus x raised power n is what? So the binomial expansion of 1 plus x raised power n is nc0 into x raised to the power 0 plus nc1 into x raised to the power 1 plus nc2 into x raised to the power 2 and so on, ncn into x raised to the power n. In this binomial expansion, if I put x equals to 1, then it becomes 1 plus 1 raised to the power n equals to nc0 into 1 raised to the power 0, nc1 into 1 raised to the power 1, nc2 into 1 raised to the power 2, and so on, ncn into 1 raised to the power n. So 1 plus 1 is 2, so it will be 2 raised to the power n will be equals to 1 raised to power 0, 1 raised to power 1, all of them are 1. So nc0 plus nc1 plus nc2 up to ncn. Please remember this formula, that nc0 plus nc1 plus nc2 up to ncn is nothing but 2 raised to power n. Right? Now, here, if I replace n by n minus 1, so it will be n minus 1 c0 plus n minus 1 c1 up to n minus 1 cn minus 1, it will become 2 raised to power n minus 1. It will become 2 raised to the power n minus 1. So, if I use the same thing, it will be nothing, but we are done. So, it is 1 into 2 raised to the power n minus 1, the number of super keys will be 2 raised power n minus. Clear? I'll give you 2-3 different approach to solve the same question. Don't worry about that. So here itself, if I ask you that, sir, what is super key? So super key will be the set containing A1 union with any subset of remaining n minus 1 attribute union with any subset of remaining n minus 1 attributes will be a super key or superset of A1, that is candidate key, and any superset of candidate key is a super key. Now the thing is, there are 2 raised power n minus 1 subsets of a set of size equals to n minus 1. Therefore, A1 can be unioned in 2 raised power n minus 1 ways. Hence, 2 raised power n minus 1 super keys. Still not clear, sir. Still struggling. Come on. Still struggling. So what is the set? So what are the attributes? A1, A2, A3, A4 up to AN. So if you define a super key, what will happen? So if you define a super key in this scenario, do you realize that A1 must be present? So A1 must be present. I'm saying don't care. Phi represent may or may not be present. I'm saying phi represent that may or may not be present. So if I ask you for the number of super keys, only one way for A1 to be present. And for A2, we'll have two choices. Sorry, may or may not be present. And for A3 also, two choices. And for A4 also, two choices. And so on. For AN also, you will have two choices. So, how many times 2? n minus 1 times 2, and this will be equals to 2 raised to the power n minus 1. Clear? Please tell me, all three observations are clear to each and every one of you? If we define any super key with respect to candidate key A1, then A1 must be present, and for every other attribute, they may or may not be present, because as long as A1 is present, it will be a super key. As long as A1 is present, it will be a super key. Okay. If you understood the concept, this will be very easy for you. Give me the answer. Simple. No issue, sir. Very easy concept. So what will be a super key? So A1 and A2 together defines the candidate key. So all attributes of candidate key A1, A2 must be present. That is, both A1 and A2 must be present, and if two attributes are gone, you are left with n minus 2 attributes, and 0 or more attributes out of remaining n minus 2 attributes. So if I ask you with respect to number of super keys will be equals to, so there is only one way to choose both the attributes, and for 0 or more out of remaining n minus 2 attributes, you will have 2 raised power n minus 2 choices. Therefore, number of super keys will be 2 raised to the power n minus 2, and this is your answer. This is your answer. No issue, sir. Okay. Okay, let's check with respect to other approach. Sir, attributes of the relation are A1, A2, A3, A4. So, if I ask you that super key with respect to candidate key equals to A1, A2. So, the idea is both A1 and A2 must be present. For A3 may or may not be present, for A4 may or may not be present, for AN may or may not be present. So if I ask you for number of super keys, so there is only one choice for A1 to be present, and there is only one choice for A2 also to be present. For A3 may or may not be, therefore two choices. For A4 may or may not be, therefore two choices. AN may or may not be, therefore two choices. We know that this is n minus 2 times 2. So this will be equal to 2 raised to the power n minus 2. Clear? Bolo ji, tell me. So there can be just one candidate key present. Frame sign. There should be at least one. 1 minute. Please wait for some time. Next question will clear your doubt. Frame sign. Next question will clear your doubt. So please, let's assume that there are two candidate keys. Consider a relation R with the same attribute, same set of n attributes. Find the number of super keys possible when there are two candidate keys in the relation. One happens to be A1, another happens to be A2. Then how many super keys are there? Frame. Think carefully. Think carefully. As of now, none is correct. As of now, none is correct. Come on, guys. If I ask you for these super keys, listen to me very carefully now. If I ask you for these super keys, what did I say? At least all attributes of at least one candidate key should be present. That means attributes of more than one candidate key may also be present. What did I say? Sir, all attributes of at least one candidate key must be present. That means attributes of more than one candidate key may also be present. Yes or no? All attributes of at least one candidate key should be present. That means attributes of more than one candidate key may also be present. So let's consider a scenario when A1 is present but A2 is not present. Or the scenario may be that A1 is not present but A2 is present. Or the scenario may be that both A1 and A2 are present. In all three cases, all attributes of at least one candidate key are present. In all three cases, all attributes of at least one candidate key are present. Yes or no? Tell me. So either A1 is present or A2 is not present. So whatever happens with remaining n minus 2 does not matter. A2 is present and A1 is not present. So whatever happens with remaining n minus 2 does not matter because all the attributes of at least one candidate key are present. All the attributes of at least one key candidate key are present. Here also, all attributes of at least one candidate key are present. Clear? So the idea is, sir, that means for remaining there will be no restriction. For remaining, there will be no restriction. So a super key will be of this type or of this type or of this type. Yes. A super key may be of any one of these three types. So I'll say, sir, with respect to this first case, there is only one way that A1 is present and there is only one way that A2 is not present. For something to be present in the set, there is only one way. For something to be absent in a set, there is only one way. But if it may or may not be present, then there will be two choices. So that will be 2 raised power n minus 2. Here also, sir, only one way that A1 is not present and only one way that A2 is present. For every other element, there will be two choices. So this will come out as 2 raised power n minus 2. So 2 raised power n minus 2 super keys are there in which A1 is present but A2 is absent. 2 raised power n minus 2 super keys are there in which A2 is present but A1 is absent. And 2 raised power n minus 2 super keys are there in which both A1 and A2 are present. So 2 raised power n minus 2. So if somebody asks me that total number of super keys, so either you can define the super keys using this concept or using this concept or using this concept. This will be 3 times 2 raised power n minus 2. Clear? Three times. Tell me, is it clear? Whosoever is giving the answer as 2 raised to the power n plus 2 raised power n minus 2, do you realize that this value will be greater than 2 raised power n? Do you realize that 2 raised power n plus 2 raised power n minus 2 will be greater than 2 raised power n? Anirudh, some other answers are also there whose value clear. So for a set containing n elements, there can be at most 2 raised power n subsets. So the number of super keys cannot be more than the total number of subsets possible. The number of super keys cannot be more than the total number of subsets possible. What else you are including? Are you borrowing from other relations? No, sir. What explanation is needed, Arush? Don't ask that, sir. Please explain once again where exactly you are not able to understand. Please let me know. What exactly you are not able to understand? Just tell me about that. Don't focus on this one. Focus on this right tick and cross. So, right represent present in the set, cross represent not present in the set, this may or may not be present in the set. How is what? How the number of super keys are calculated? That's what I am explaining. That all the candidate keys of at least one, all the attributes of at least one candidate key should be present. That means either all the attributes of A1 first candidate key A1 should be present, or all the attributes of A2 should be present. Sir, we say that all the attributes of at least one candidate key should be present. That means all the attributes of more than one candidate key may also be present. So here, all the attributes of exactly one candidate key are present. Here, all the attributes of exactly one candidate key are present. Here, all the attributes of more than one candidate key are present. Apart from that, you have zero or more attributes of the remaining attributes. You don't understand because you don't listen to me carefully in the very first time. Somasekhar, you tell me how it is not for A1 or A2. Somasekhar, you tell me how it is not for A1 or A2. Don't ask wrong question. First ask yourself how it is not for A1 or A2. You tell me how it is not for A1 or A2. Tell me, Somsekhar. Spoon feeding. You need spoon feeding. That, sir, I'll ask something, you'll answer. You answer my question. How it is not for A1 or A2. Okay, sir. This is something when you run away from the problems. है ना? You are completely reliable on me that I'll ask something, he'll answer. If he answer, that's okay. If I'll ask a question, if he answer, if I get it, that's okay. Otherwise, also it's okay. These are the super keys in which A1 is present but A2 is not present. So these are the super keys that contains the exactly one super key, that is A1, but none of the attributes or of other super key are present. Right? And here A1 is not present but A2 is present. So these are the super keys in which only the attributes of candidate key A2 are present. And this are the super keys in which attributes of both A1 and A2 are present. What else can be done? So A1 or A2 or is or allows you to be true when both of them are true. That means both A1 and A2 may also be present. Okay. Let me you you a easier version of the same thing. Principle of inclusion exclusion. Don't know. Let's assume that this is a set A. This is your set B. And this is nothing A intersection B. Set containing common elements of A and B. If I ask you, let's assume NA is the number of elements in A. NB represent the number of elements in set B, and A intersection B represent the number of elements common to set A and set B. If I ask you how many elements are there in the union of A and B, so in the union of A and B, the common element should be calculated only once. In the union of A and B, the common element should be calculated only once. Yes or no? So how do we define principle of inclusion exclusion? Sir, the number of elements in A union B is, sir, include the number of elements of set A and the number of elements of set B. So when you include the elements of set A and also include the elements of set B, then the elements that are common in A and B have been included twice. The elements that are common in A and B are included twice, but you should include them exactly once. Therefore, once you have to subtract the elements that are common between A and B because they must have got added only once. This one you all remember? 10th class mathematics. Now don't tell me that, sir, we don't know this. Else I cannot help if you don't know this. This is 10th class mathematics. Even if you are a diploma student, then also you must know this because this is from 10th class. Correct? So now try to solve this problem using this particular concept. If I ask you this, let's assume that these are the super keys that contains attribute A1. Let's assume this are the super keys that contain all the attributes of candidate key A1. These are the attributes. So, sorry, these are the super keys that contains all the attributes of candidate key A1. Clear? And let's assume these are the candidate keys that contains all the attributes of candidate key A2. So these are nothing. So let's say that this set represents the number of super keys. This set represent the super keys that contains all attributes of candidate key A1. And this is the super keys that contains all attributes of candidate key A2. Now there will be some super keys in common. That means some super keys that contain all the attributes of candidate key A1 may also contain all the attributes of candidate key A2, and super keys that contains all the attributes of A2, some of them may also contain all the attributes of candidate key A1. Yes or no? So what are this? Sir, these are the super keys that contains all the attributes of both candidate keys A1 and A2. Clear? Now I ask you, how many super keys are there that contain all the attributes of set A1? How many super keys are there that contains all attributes of candidate key A1? Tell me. So this is, let's say, NA1 represent number of super keys containing A1. How many super keys, how many such super keys will be there? Sir, A1 is guaranteed, and for remaining n minus 1 attributes, you will have 2 raised power n minus 1 choices. Right? Now, if I ask you that this is NA2, is number of super keys containing A2. Will be equals to 2 raised power n minus 1 only. Now, let's assume these are the number of super keys containing both A1 and A2. So, how many super keys that will contain both A1 as well as A2? Number of super keys containing both A1 and A2. Sir, A1 and A2 both should be present. So, for each of them, you will have one choice, and for remaining n minus 2 attributes, you will have 2 raised power n minus 2 choices. So, if I ask you how many super keys are there containing A1 or A2? and it will be calculated exactly once. So this we have already defined that, sir, it will be nothing but number of elements in set A1 plus number of elements in set A2 minus the number of elements in A1 intersection A2. So we know it will be nothing but 2 raised power n minus 1 plus 2 raised power n minus 1 minus 2 raised power n minus 2. If you solve this, you can write 2 raised power n minus 1 as 2 times 2 raised power n minus 2 plus 2 raised power n minus 1. Again, you can write it as 2 times n minus 2 minus 1 times 2 raised power n minus 2, right? So this is nothing but 2 times 2 raised power n minus 2. This is also 2 times 2 raised power n minus 2. This is 1 times 2 raised power n minus 2. So 2 plus 2, 4 times 2 raised power n minus 2 minus 1 times 2 raised power n minus 2 will be 3 times 2 raised power n minus 2. Clear? If it is clear, you have some homework problems. This, this, this. So 3 different homework, 4 हैं, but one is okay. So one A1 A2 together is one candidate key, A3 A2 A3 A4 together is another candidate key. Here A1 A2 together is one candidate key, A2 A3 together is another candidate key. Here A1 is one candidate key, A2 is another candidate key, and A3 is another candidate key. So you need to solve them. One, if all the attributes in itself, if every attribute of relation R is a candidate key in itself, then how many total super keys are possible? Clear? So these are the homework problems for the next class. We'll discuss this thing, questions in the next class. So that will be all for this session. If you have any doubt, you can ask. Anyone who is struggling with the concept of finding the number of super keys, it is my humble request that go home, listen to the lecture once more if you are not able to understand in the one go, and then try to solve these homework problems before you attend the next class, so that if you have committed any error, you will be able to analyze them and you will be able to ask them during the class. After that, I will not discuss anything related to number of super keys. We cannot do same thing every day. So, any doubt? Any doubt? Please tell me. Varnekar ji, you need to join the class at proper time. Otherwise, don't ask the questions in between. I cannot answer the same thing again and again because it is wastage of time for other students. In the very past go, I'll never say no to any doubt. But once it has been explained, you cannot ask the same thing again at some other time. Okay. Thank you very much. See you tomorrow with this homework question, and then we'll see the relation between two FD sets. That what type of relationship can be defined between two different FD sets. So that will be the content for the next class. That will be all for this session. Thank you very much.